Alright, so this is Dr. Sweeney, and we're going to look at the second part of our work inside of vectors and vector spaces. And this one is going to be on vector spaces and subspaces. Now, vector spaces and subspaces are theoretical constructs. They have a set of definitions, and what we're going to do for this one is we're going to look at vector spaces in R2, alright, to help us demonstrate the axioms and properties of vector spaces, and to kind of demonstrate for people and show them what it is that we're looking at when we do look at a vector space. What you want to remember is that R2 is just an example of a vector space. It's not all vector spaces, just in general, and so consequently we want to be really careful or really clear about that fact. Okay? So by definition, what makes a vector space is that it has two properties. It is closed under addition, that is vector addition, and it is closed under scalar multiplication. So now what we need to get is what does it mean to be closed under addition, and what does it mean to be closed under scalar multiplication. So what we're going to do is we're going to let V and W belong to, and that's what that means, belong to our vector space V. And we're going to use this capital letter V, and we want to be careful that this is not a matrix. This is actually the vector space. We call the vector space V. Okay, that vector space V. Then V plus W is going to belong to V. Right? So what that means is that if I have V and W, okay, and they belong to V, then if I add the two of them together, then I'm also going to get something that belongs to V. Okay? So let's take an example. If we let V, or we're going to let big V equal R2. So that's going to be the example of the vector space that we're going to be using. And we take V, okay, equal to, let's say 3, -1, and W equal to 5, 2. And we add them together, then V plus W, okay, you can go ahead and do this on your own, is going to end up being 8, 1. 8, 1 is in R2, right? Because it's got two components, and both of those components are in the reals, right? V plus W belongs to R2, all right? And you can kind of actually see that this is going to be the case for any set of vectors. Imagine what happens when you add two real numbered components, right? 3 plus 5, right? Or E plus pi. E plus pi is still real. And our second set of components, if we add those together, we're also going to get another real number. And how many of them are we going to have? We're going to have two of them, right? Okay, so you add two real numbers together, you get another real number. And if you've got two components in the starting vectors, you're going to have two components in the ending vectors. Okay? And so that's what we mean by closure under addition. There's going to be different ways that we go through and we actually show that we have closure under addition, but oftentimes what we'll say is we'll just say that this thing here is a vector space, and if we say this thing is a vector space, like R3, or we'll talk about sets of polynomials, what that really means for us is that in fact, we have closure under addition. Add any two of them, and you're going to get another vector in the space. Okay? Now let's talk about closure under scalar multiplication. If we let V, right, belong to V, that's our vector space, and S, and it's gonna belong to a field. I don't want you to worry too much about F being a field, all right? For our purposes for this class almost exclusively, we're gonna have all of our scalars be real numbered scalars, but they could be complex. You could have complex scalars. We will see a little bit of that. And it's theoretically possible to have other kind of scalars, but for our purposes, we're gonna have like S belong to the reals, okay? Then SV, when we multiply by the scalar, is going to belong to V. It's going to be part of the vector space. So like let's say, for example, we take V is equal to R3 now. Okay? Those are the three-dimensional vectors. And we'll let S belong to the reals. All right? Or S equal the reals. Like I said, we're pretty much always going to have that. And if it isn't stated already, just assume that that's the case. Okay? Excuse me, that's my field. All right. And so what I'm going to do now is I'm going to say, okay, well, let's say, for example, I take 5 times 1, negative 1, 2. What you're going to notice is I take a real number times a real number, and that gives me another real number. Real number times a real number, that gives me another real number, another real number. And how many components do I have? There are 3 components. So in this case, if I took, right, if I said 5 equals S and V equals 1, negative 1, 2, then you'll see that SV, right, is going to belong to R3. Imagine that's the case for all of them, okay, for all of the vectors in R3. All the vectors in R3 have 3 components. We multiply them by the scalar that's in the reals. We're going to get another real number. And so consequently, that shows that in this case, R3 is closed under scalar multiplication. And for our purposes, what we really want is we want to say, okay, if I say that R3 is a vector space, that means it's closed under scalar multiplication. That is that I can take a vector in the space, right, okay, times any scalar, and I'm going to get a vector in that space, or in this case, R3. And that's scalar closure under scalar multiplication. These 2 requirements, they are the requirements for us having a vector space. Everything that we get from here on out is going to be a property that is a result of this closure under addition and the closure under scalar multiplication. So we'll start with the properties and look at the properties. We're going to draw out the properties to think through them, but they're all a result of closure under addition and closure under scalar multiplication. So now let's look at the properties of vector spaces. The first one that we're going to be looking at is commutativity of addition. And commutativity of addition is basically that we can add any 2 vectors in any order and we'll get the same vector, that we're going to get actual equality. So I'm going to go over and I'm going to say, okay, I've got 1, 2. All right, well, let's see this in action. So I've got V equals, let's say we'll make it 2, 1. And we'll let W equal 3, 5. Okay, 2, 1 is 1, 2. And then we'll go 1, 2, 3, 4, 1, 2, 3, and then 1, 2, 3, 4, 5. And there's 3, 5. And so our resulting vector is this vector right here. Okay? Or we could go 3, 5, 1, 2, 3, 1, 2, 3, 4, 5. And then up to 1, right? Go 1 over 2, 1, 2, and up 1. And we end up at the same place. And you could try it algebraically as well, right? 2, 1 plus 3, 5 is going to end up being 5, 6. That's V plus W. And then when we do the addition as well, we're going to get W plus V. And that's going to equal, well, that's going to then be 3 plus 2 and 5 plus 1, which ends up equaling, guess what, 5, 6. So we end up getting the same value whether or not we go V plus W or W plus V. And that's commutativity of addition. Now let's take a look at associativity of addition. So associativity of addition is going to be U plus V, and let's say we did that first. We'll put that in parentheses, plus W equals U plus, and let's say, for example, we did V plus W first. So basically, it's like associativity that we had before, okay? It just means that we can, in fact, if we add a certain set of vectors first, right, and then add another vector to it, we can either add that vector first or do that vector first, do that vector second, okay? So like, let's say, for example, we take U equal to negative 1, 2, V equal to 3, 4, and W equal to 2, 5. So U is negative 1, 2, so that's this vector right here, okay? And we're going to add to it V, so that's going to be 1, 2, 3, 1, 2, 3, 4. And so our resulting vector is going to be this red vector right here. That's U plus V. Then we'll add to that 2, 5. 1, 2, 1, 2, 3, 4, 5. There we go. There that is. And so our resulting vector is going to be this blue vector, right? Almost on the exact same line. It's fine. Is that there? That's the blue vector right there. Now go in and see if you can do u plus v plus w. So meaning you're going to do v plus w first, and then do u. Okay, and then add u. All right. So to pause the video for a moment, and then let's go and do that. Okay. So we'll start out with v plus w. Okay. So v plus w is going to be 1, 2, 3, 1, 2, 3, 4. So there's v plus w. W is now 1, 2, 1, 2, 3, 4, 5. Okay. And so there's our resulting vector. There's v plus w. We'll write that in green. There's the green one. Okay. And then we're going to add u to it. So u is negative 1, 2. There's u. And there we go. You can see, once again, we've got the blue line. We've just gone in a different direction to get there. Okay. So the green line here, that was v plus w. We did v plus w first because it was in parentheses, and then we added the u. And that's associativity of addition. This next axiom is going to end up being really super important. And this is that there is the existence of the zero vector in every vector space. So every vector space requires the zero vector. Now, we're going to write in every vector space, we're going to represent the zero vector as that. Okay? Make that black. As it'll be just 0 with the vector sign over it. That's the zero vector. Now, that doesn't necessarily mean that it's going to be like a vector in R2 or R3. It depends upon the particular vector space you're looking at. Each one of them has kind of a slightly different zero vector. But that zero vector all has the same set of properties, and that is essentially that if you add the zero vector to anything, right? If we take v plus the zero vector, what we get back is we get back v. It's what we call an additive identity. Okay, that is that if I add the zero vector to any other vector, I get the same vector back. That's the additive identity. The existence of the zero vector actually follows from the fact that 0, right, belongs to, say, for example, in our case, the reals. All right, and since R2, say, for example, is closed under multiplication, under scalar multiplication, right? By property, 0v is just going to end up equaling that zero vector. It's going to zero everything out, okay? And so closure under scalar multiplication ends up giving us the zero vector. You're also going to see that when we have closure under addition and the fact that we can generate linear combinations is also going to give us the zero vector in any space. And the zero vector is in Rn. The zero vector is the origin, okay? And it has no length, and this is going to be important, it has zero dimension. Every other vector is going to be one-dimensional. Every other single vector is going to be one-dimensional, right? But the zero vector actually has zero dimension. It doesn't have length, it doesn't have width. It's the only vector that actually is simply a point, okay? So it's zero-dimensional, right? Versus, like I said, every other vector is going to end up being one-dimensional. And so this zero vector is going to end up becoming really, really important. This next property, which is actually property number 3, is the existence of additive inverses. So an additive inverse is, in our case, it's going to be a vector w. So we're going to let v and belong to v, okay? And we're going to say that w is the additive inverse of v if v plus w equals 0. Well, you might be thinking to yourself, well, the most obvious thing to do is to just make w the negative of v. And that's exactly right. That's exactly what we're going to do. So we're going to see that v plus negative v, right, is going to equal 0. So in any vector space, that's going to be the case. negative v exists because negative 1 times v is simply equal to negative v. So closure under scalar multiplication allows us to show that negative v exists, okay? And then addition, right, okay, gives us back the zero. Addition, we know closure under addition, so when we add the two of them together, we end up getting the zero vector. That's it, right, okay? So like say, for example, if I take v equals 1, 1, okay, v equals 1, 1, and so negative v is going to equal negative 1, negative 1. If we do this geometrically, let's take, we're going to take red. So 1, 1, that's v. And then negative 1 is going to, we're going to do tip to tail. That's 1, 2. 1, 1, there's v. And negative 1, there's v as well, or that's negative v, okay? And when we add the two of them together, what did we get? We got back to the zero vector, right? So there we are, big green, zero vector, okay? Took v out, negative v back, we ended up getting back to the zero vector. And so that's basically what an additive inverse is. Additive inverses exist because we're closed under addition, okay, and closed under scalar multiplication, and we have a zero vector. Nice. Next up is the unit property. And so the unit property is basically just this. We're going to do this in black. It's going to end up being 1 times v equals v. It seems really obvious, but when you're being mathy people do things like this. They're like, yeah, 1 times the vector is itself. That's kind of important. Okay? Essentially what the unit property tells us is that there exists something like a multiplicative identity. Okay? This is the multiplicative identity. That is that we have a number that when we multiply by a scalar and use scalar multiplication, what we're going to get back is we're going to get back the original vector. So now we have the associativity of scalar multiplication. And what that states is that we've got R and S, they're going to belong to, let's say, for example, in our case, the reals. Okay, so we'll take our vector spaces over the reals, and we'll have V, let's say, for example, is going to belong to our vector space V. Okay, which, let's do, in our case, we'll do R3. Because we're going to do this one algebraically rather than geometrically. So what this is that this is RSV is going to equal RS times V. Okay? So what that means is that I can multiply the vector by a scalar and then multiply by another scalar, and that's the same thing as if I multiplied R times S, okay, and then multiplied it by V. What this is going to basically allow us to do, it's going to allow us to do some kind of like factoring from individual vectors. So let's say, for example, I have R equals 3 and S equals negative 1, okay? And then we'll let V equal 1, negative 1, 2. We'll have that be vector V. Now, if I take RSV, that's going to be 3 times, and we'll do this in parentheses, negative 1 times 1, negative 1, 2. And so that'll end up being 3 times negative 1, 1, negative 2. And that ends up equaling negative 3, 3, negative 6. Now what you want to notice is that actually I can pull out, if I wanted to, I can pull out negative 3 out of all of these and make this negative 3 times, and then what I'm going to do is a factoring here. And that algebra, the factoring, it works when we're working in vector spaces and working with vectors, we can factor out values, okay, very naturally, same way that we do with, let's say, for example, a polynomial. What you're going to do, though, is you're going to factor each term, okay, or each a value out of each term, the same value out of each one of the terms, and then that becomes your scalar. So negative 3 will divide this negative 3 by negative 3. That's going to end up being 1. Then 3 by negative 3, that's going to end up being negative 1. And then negative 6 by negative 3, that's going to end up being 2. And then we can rewrite this as 3 times negative 1 times 1, negative 1, 2. Okay? So these properties of scalar multiplication, they're going to actually really allow us to do a lot of really cool algebra that's going to be very handy and very valuable for this entire chapter. And so that's our associativity of scalar multiplication. So now let's talk about the properties of the zero vector. And so the zero vector is something that we really need to talk about when we talk about vector spaces because of its primacy, how important it ends up being whenever we talk about or do any work with vector spaces. So the first thing to get is that the zero vector is in fact unique. All right? What that means is that there's only one zero vector. Okay, that's the idea. Only one zero vector in any vector space. This ends up becoming really important because at least, whenever mathematicians argue, they argue about things like, well, what if we had more than one zero vector? And you might think to yourself, well, that would be silly. But it does happen. There are different kind of spaces where we in fact have more than one zero, right? Say, for example, things that are modulo 4, for example, where 4, 8, 12, they're all zeros, right? Everything, all of those values zero everything out. But in a vector space, we're only going to have one zero in any vector space. 2, we're going to 0v equals 0 for all v. Okay, there we go. Equals the zero vector. So if you multiply 0 times the vector v, any v in v, okay, in our vector space v, then what we're going to get is we're going to get back the zero vector. That's going to happen each and every single time. Look at number 3, okay? K times the zero vector is going to be the zero vector. So if you scalar multiply by the zero vector, you're going to end up at the zero vector, okay? So basically, we can't stretch the zero vector. So no stretching the zero vector. It just ends up giving us exactly what we had before. So none of that. Not allowed. Okay? 4, okay, the additive inverse, negative v, is unique, right? There are no others for all v in v. So choose any vector v that you want, okay? There's only one additive inverse for it. And it is negative 1 times that vector, okay? Which, by the way, is our 5th axiom, which you're like, hey, didn't we just talk about this before? And the answer is, yeah, totally. But so for all v belonging to v, okay, negative v is equal to negative 1 times v. All right? It does exactly what you think it is. Right? Scalar multiplication by negative 1 gives me the additive inverse. And then 6, we get if k is a scalar, right? So k belongs to our field f, okay, and v belongs to v. That's our vector v belongs to the vector space, such that kv equals 0, then either, right, one of the two of these has to be true. K has to equal 0, or v has to equal 0, okay, the zero vector. So it doesn't necessarily have to be both, but it has to be one or the other. Either one. Okay? So if you multiply a vector times a scalar and you get the zero vector, what that tells me is that either k is 0 or v is 0. This is going to come into play when we talk about things like, well, we're going to say that v is not the zero vector. Well, if v is not the zero vector and we get kv equals 0, that means that k's got to equal 0. Okay? Or we might say something like, the scalar k is not 0, but v is, but kv is 0. Well, that means that v has to be the zero vector. So it becomes like kind of a force. It seems really obvious to see it now, but you want to remember that, like, logically speaking, something like this could become really important if we're working through proofs and we're doing some different work. Like if we're doing, proof work, or we're trying to show that something in fact is true. All right, so one of the things that I want you to get and to understand here is that what we've done here is we've demonstrated the properties of vector spaces from the perspective of R2 or R3. Not all vector spaces are in Rn or are Rn. We can see some that are going to be polynomials. We're going to see some that are going to be matrices. We're going to see some that are going to be like functions and what we call function spaces. And these are vector spaces, okay? And so they're important things to think about. But no matter what vector space you're looking at, if it's defined as a vector space, it has all of these properties. It starts out with closure under addition and closure under scalar multiplication, okay? And then it gets all of the other properties associated with it. So we can do all the same algebra on it. You're going to see that this is going to become incredibly crucial when we do things like differential equations, right? Okay, or we might do this also with polynomials, and polynomials become a very special group of vector spaces called PNR. Okay, and so when we start talking about subspaces, what I want you to get is I want you to get that subspaces are defined as subsets of vector spaces that are themselves vector spaces, right? So they have all the properties of vector spaces. They get all the things that we just talked about inside of the last half hour. So now let's talk about subspaces. And so a subspace we're going to call S. S is a subspace of a vector space V, okay? And so S is a subspace of a vector space V. So, if 1, S is a subset of V, and let's talk about what it means to be a subset of V. Okay, so a subset of V, say for example, is if V belongs to S, then V also belongs to V. So basically, if we have V is an element inside of my subspace S, then it's also going to be an element in V. Okay, right? So like for example, if we have right, S equals the set of all vectors S times 1, 0, okay, for S belonging to the reals. So what we'll do is that's all the scalar multiples of 1, 0. So all the stuff in S belonging to R, are going to be S. So it'll be like 1 times 1, 0. That equals 1, 0. 0 times 1, 0. That equals 0, 0. Pi times 1, 0, right? That equals pi 0, okay? And so consequently, we've got 1 times 1, 0, 0 times 1, 0, 0, 0, right? Pi 0. Notice that each one of these, right? Okay? This belongs to, what? R2. 0, 0 belongs to R2. Pi 0 belongs to R2. Okay, each one of them belongs to R2, right? And you can imagine that if I took just ZS times 1, 0, this ends up equaling S0. And since S belongs to the reals, S0 also belongs to the reals. So that also belongs to R2. Okay, so everything in S, everything in that set is also in R2. So S is a subset, not yet a subspace, but a subset of R2. Okay? S is a subset of R2. So that's the first requirement for S to be a subspace of V. The second requirement is S is a vector space. So that's the second requirement for S to be a subspace. Okay? So, for S to be a subspace, S has to be a vector space. And what that means for us is, 1, S is closed under addition. So that's our first requirement. So let's take, for example, the example that we have above. So we'll take, like, we're going to let V and W, two vectors, belong to our S here. Okay? So what that means, I'm going to go through and I'm going to define them. That means that V equals, let's let it be the scalar V, 1, 0, plus, and then W is going to be W times 1, 0. Or excuse me, not plus, but, and W is going to be W times 1, 0. So that's equal to W, right? And that's because both V and W are in S. This is the definition for elements in S, okay, for anything that's in S. So now when I go in, I'll add V plus W. So V plus W right, is going to end up equaling V0 plus W0, and that equals V plus W 0. Okay? So V plus W 0, so what you can see here is, since V and W are both real numbers, V plus W is going to be a real number. Okay? So V plus W, the vectors, are going to belong to R2. Or excuse me, not to R2, but belong to S. Because they have the same form. They're a real number, right, over 0. Or some scalar over 0, right? They're going to equal, and remember this property, V plus W times 1, 0. See that? There it is. That's our definition for S. So hence, they both belong to S. And so what we say is that S ends up being closed under addition. If I take two arbitrary vectors, V and W, okay, and I add them together, do I get another thing that's actually an S? And the answer is yes, I do. Okay? How about the second requirement here for a vector space is, remember, S is closed under scalar multiplication. So that's the second requirement for a subspace. Okay? And so when we look at S is closed under scalar multiplication, what that means is that if I take S times V, that's also going to belong to V. Or excuse me, it's going to belong to S. Pardon me. For all V belonging to S. Now we're not talking about the original vector space, we're just talking now about the subspace. So we'll let V, right, equal, we're going to have it be V0. Okay? And S is going to belong to the reals. So any scalar. And what we get now is we're going to get S times V0. So that's SV. Is going to equal SV0. Okay? And actually, trivially, this ends up being SV times 1, 0. Remember, now we can actually go through and we can factor out both of those scalars. We did that inside of one of our axioms before. And so consequently, we get this thing, SV times 1, 0. And by definition, when we go back up and we look at it, we see, oh yeah, that's the definition of being in S. To be in S, you've got to be a scalar times 1, 0. Well, there it is. There's the scalar times 1, 0. So what we get is that SV also belongs to S, to our subspace, or now our subset. So now what we have is we actually have S, right, is a subspace. Right? Because, one, S is a subspace of, of R2. So S is a subspace of R2 because everything that's in S is also in R2. Okay? And S is a vector space. Right? S is closed under addition and it's closed under scalar multiplication. Sweet. Okay? So, what I want to do now is I want to give you an example of a really important subspace. And this really important subspace is something called the null space of the matrix A. Okay? All right. So we've got the null space of the matrix A. And the null space of the matrix A is the set of all vectors. Okay? So we'll call this S again. And it's going to be the set of all vectors V, okay, belonging to, in this case, how about we'll do set of all vectors V belonging to V, such that AV equals 0. Okay? So like, for example, one thing that we know is we know that the 0 vector is trivially in there. Okay? So let's say, for example, I have A equals, and I want 1, 3, -1, -3. And I know that if I take the 0 vector, I know that 1, -1, 3, -3 is times 0, 0 is going to equal 0, 0. Okay? So 0 is going to belong to S, to this null space for A in this case. Okay? So that 0 vector is also in S. But there might be other things inside of there as well, right? Because we've seen previously that you can in fact have an infinite number of solutions to AV equals 0, right? And we might ask ourselves, well, okay, if that's true, right, what are the other things that might be in S? Okay, some of the other things that might be in S. So what I would do is I'm going to go and I'm going to solve AV equals 0 in this case. Or I'm going to row reduce 1, 3, negative 1, negative 3, 0, 0, and see what my solution is. My RREF of AV, or of A0, the RREF of A is going to end up equaling 1, 3, 0, 0. And so when we go through and we actually solve that, what we'll get is we'll get that V, my vector V that I am solving for, is going to end up equaling negative 3, 1. Okay? And in fact, what we're going to get here is that any scalar multiple of negative 3, 1 will work. Right? So we can choose negative 6, 2, for example. Or we can choose negative 4.5, 1.5. Right? Any scalar multiple of negative 3, 1 is going to work. Because if you remember, we actually are going to multiply that by a parameter, call it parameter S, because it turns out that x3 is free. Okay? And so consequently, any scalar multiple of negative 3, 1 is in fact going to be in this thing called the null space of A. All right. Now, I have another video in which I actually go through and show how it is that we solve the null space. I go through this more in depth, but I wanted to kind of just show right now what the null space is. Okay, so inside of this set S is essentially, if we wrote it in like some kind of notation, it's going to have the set of all vectors S, negative 3, 1, such that S belongs to the reals. Notice that the 0 vector is going to be included in there, because the 0 vector is just simply 0 times negative 3, 1. Okay? Now, you can go through, and we'll prove later on, that this set is a subspace. We know that it's a subset of R2. Okay? Subspace of R2. We know that it's a subset of R2. All right? We also know that S is a vector space, or that you can go through and prove that S is a vector space. 1, because it's clearly closed under scalar multiplication. But 2, it's also going to be closed under addition. That is, if you take any two vectors in the space, what you're going to get is you're going to get another vector that's in fact inside of the space. It'll work out really quite nicely. Okay? What I'm going to show right now is I'm going to show, in fact, that the null space, I'm going to use I'm going to do some proof work to show that the null space is also in fact a subspace, right? Just to demonstrate this idea of subspace. So, all right, let A, let A be an n by m matrix, or m by n, excuse me, m by n matrix. All right, okay. So, define, right, AV equal to 0, right? And so V is going to belong to, in this case, let's say, for example, it's going to belong to it's going to belong to Rn. And 0 belongs to Rm. All right? So V belonging to Rn, that's because we have n columns, right? So if you have n columns, that's going to define the size of the vector that you're going to be multiplying by, right? So this is m by n, this is times n by 1, and that gives you a 0 vector, which is going to end up being m by 1. Okay? And so that defines for me that V is going to belong to Rn. Okay? Now, I'm now going to take this and I'm going to take AV equals 0, so we're going to let V and W belong to Rn. Okay? And then we're going to take A times V plus W. We'll add the two of those together, A times V plus W. And if you remember when we do scalar multiplication, this is going to be AV plus AW. Okay? Now, the other piece that I want here is I want that V and W belong to the null space of A. So they're going to be inside of the set as well. So we're going to define that they belong to the null space of A. Well, if they belong to the null space of A, what that means is that means AV, right, equals 0, right, for V belonging to, in this case, Rn. And so that means AV equals the 0 vector, and AW equals the 0 vector. So we have 0 plus 0, just a substitution straight from the definition, right? We know that both of them are in the null space of A. So consequently, when we multiply them by A, we're going to get 0 back. So this gives me then the 0 vector when we add the two of them together. What does that mean? That means that AV, A times V plus W, okay, right, equals 0. So V plus W, right, when we multiply by V plus W, we also get the 0 vector. So that belongs to the null space of A. Awesome. So null space of A is closed under addition. Awesome. That's good. It's handy. Also, if I take A, now I'm going to prove scalar multiplication. So we're going to let S belong to the reals, okay? And V is going to then belong to the null space of A, okay? Belong to the null space of A. So now I take A, SV, okay? That's going to end up equaling S times AV, because we can actually just pull the scalar out. And since V is in the null space of A, this is going to be S times 0, the 0 vector. And remember that property that we had, anything times the 0 vector is the 0 vector. Well, since I multiplied A times SV and got the 0 vector, that means SV belongs to the null space of A. So, null space of A is a subspace. Awesome. So what we've shown, right, we picked out two vectors that were in Rn. We show that they actually have to be in Rn because if we're multiplying by V, right, m times n end up by 1, okay, they've got to be in Rn, all right, is a subspace, we should say subspace of Rn. Excuse me, that's important. So we can see all these vectors V that we're going to be multiplying by, they're all in Rn. They've got n components, they're all real numbered. If I add any two of them together, I get the 0 vector. I get something that's also in the null space, right? I multiply A by that addition, I get 0. Awesome. Or I get closure, and so that's closure under addition. If I multiply any vector that's in the space by a scalar, I'm also going to get the 0 vector when I multiply that by A. So that scalar multiple is also in the null space of A. So the null space of A then is a subspace of Rn. And that's super valuable. So this completes our talk about vector spaces, and it at least starts us out on understanding of subspaces. Subspaces are going to become very valuable for us because what we're going to do is we're not only going to want to know things about vector spaces and certain objects in vector spaces, but oftentimes we want to define like a whole set of solutions to differential equations, or a whole set of solutions to a system or to a homogeneous system in terms of whether or not they're actually a vector space. Do we know that they're closed under addition and closed under scalar multiplication, right? Because if they are, then what we end up with is we end up with something that's incredibly valuable for us in terms of doing mathematics, right? It'll allow us to, kind of say, to generalize across a lot of different cases and scenarios about certain things. Like, for example, when we look at this null space, the fact that the null space of a matrix A is in fact a subspace, that it is in fact a vector space for Rn, is way powerful because it allows us to say, you know what, if I take any two vectors that are in the null space, I can add them together, they're also going to be in the null space. I also know that if I multiply by a scalar, it's still going to be in the null space. So this allows me to do a lot more mathematics, and it actually also allows me to kind of define what sorts of vectors, right, that I can multiply A by and end up zeroing them out, right? And if you kind of think algebraically about that, or maybe even practically, that could end up being very, very beneficial, very powerful, okay? All right, so big things or big key takeaways for this particular lecture is that we have this thing called a vector space. It's closed under addition and closed under scalar multiplication. And then we have these properties that allow us to do both geometry and also algebra, right? They allow us to do powerful things with anything that's in the vector space. We've got some notation. I want you to pay attention to the notation that's inside of the lecture, okay? And there's a lot of actual kind of vocabulary, and you want to make sure that you are being clear on what the vocabulary is, because we're starting to expand out that vocabulary. The entirety of this chapter is going to have a ton of vocabulary. You're going to be speaking an entirely new language, and that new language starts out with this idea and this definition of the vector space.